Welcome to normal distributions and using the z-table. The z-table is used when in the question it describes the population as being normally distributed, or the other thing that you've noticed is that there's a lot of information that has been collected, say over 25. And this can be approximated by the normal distribution. So before I go further on, please make sure you hit a like so I can tell my daughter I'm a YouTube creator and I can brag to my coworkers about how many likes I get. So let's get started with an example. So if we have the z-score, which is equal to x minus mu over sigma, x is described as the boundary condition. It's the number that we're checking against. It's often the number that's given to us in the question. Mu, which looks like a U with a long tail in the front, is described as the population average. If you're lucky, it's given to you in the question. If you're unlucky, you're going to have to figure it out. And sigma, which is on the bottom, looks like an O with a tail on the end on top of it. It stands for standard deviation. Again, if you're lucky, the standard deviation will be explicitly told to you in the question. If you're unlucky, you're going to have to figure it out. So now let's look at a problem. A public health nurse knows that 1 in 15 individuals that come to be tested for hepatitis C will have a positive result. If 120 people are tested, what is the probability that at most 15 will test positive? The wording of this question is a little difficult, so let's take a look at that. Because of the number of people tested, 120, it's probably normally distributed. There's other conditions that we need to check, but based on it being a large sample size, it's probably normally distributed. So most likely we're going to have to calculate the z-score, which is z is equal to x minus mu over sigma. Mu, as you remember, is the population average, which if we're lucky, we're given it. It's not expressly given to us in the question. And sigma is the standard deviation, which again, if we're lucky, is given to us. But unfortunately, no such luck in this question, so we are going to have to figure it out. However, let's talk about the good news. It says at most 15. This is our boundary condition. So our x is equal to 15. At this point, we need to talk about continuous data and discrete data. So in this particular case, it's 15 continuous. So continuous data are numbers that make sense to have a decimal. So for instance, 15.2, 15.3, 14.9, 14.91, that is continuous data. Discrete data is data that makes no sense to have decimals. So for instance, you don't have 15 and a half people. You don't have 12 and a half hot dogs in a package. They're only whole numbers, no decimals. Now in this case, we're talking about individuals. So it does not make sense to have 15 continuous. That doesn't make sense. The number that we're going to use would be 15.5. We use the 0.5 to make sure that we include the 15 because at most we have 15. So in this case, because it's discrete data, we're going to use x is equal to 15.5. As noted earlier, we don't have mu. It has to be calculated. So mu is equal to n times p. So mu is equal to 120 times p. But what is p? P is the probability that you test positive. So 1 divided by 15, which is going to equal 0.066666666 repeated. I'm just going to round it to 0.06667. And now I can calculate my mu, which is equal to 120 times 0.0667, which is about equal to 8. Also, we're not given our standard deviation, our sigma, which is equal to the square root of n times p times q, where p is the probability that it will happen, q is the probability that it won't happen. So 1 minus P is the same thing as Q. And a little bit of plug and chug, you just put in 120, the 0.06667, and 0.93333. That ends up being 2.73. If you look at our z-score formula, which is the boundary minus the average over the standard deviation, so 15.5 subtract 8 divided by 2.73, that equals 2.747, which we're just going to round it to 2.75. This is not the probability. It is simply where to look on the Z table. So we go down 2.75 and we go across 0.05. And we read the probability at that point as being probability is equal to 0.9970. So if we look at a sketch of the normal distribution graph, the 15, which is here, the normal, which is 8, is here. That means that 99.7% of our data is less than 15. I apologize, in the slide before I noticed that I wrote down 1 minus Q. It should have been 1 minus P. I said the right thing, but I wrote down the wrong thing. And I'll say it one last time, please make sure you hit a like so I can brag. I'll talk to you soon. I hope this helped.